Hello. So this question is about related rates, and we've been given some information about liquid going into and out of a cone. So this is quite a long question. I've actually just written out my answer, and I'll just step you through that. So the first thing I've done is actually just pick out all the information that's in the question and write it down and draw a few diagrams. So what we know from the question is that we've got a cone with a radius of 2 centimeters and a height of 10 centimeters. And I can get a little bit more information from that as well. You can see I've drawn an angle at the point here, and I've calculated the diagonal length just using Pythagoras, and some trigonometric ratios for that angle in the corner. Those will be useful in a moment. What else have we been given, which is that the amount of liquid leaving the cone is proportional to the surface area that it's in contact with. So that's this formula which was given in the question. And when we have some kind of proportional relation, I can say that they're equal with some kind of constant in front. So this is the rate at which the liquid is leaving the cone. We're also told that some liquid is being added to the cone at a specific rate, and that's 1 cubic centimeter per minute. So using those two pieces of information, we know that the change in volume of liquid, so the amount of liquid going in minus the amount of liquid going out, would be this this expression, so dV dt, the change in the volume of liquid. Obviously, if that value is positive, then the liquid will be increasing. If it's negative, it's decreasing. We're also told that the height of the liquid is decreasing, and that's decreasing at a rate of 0.1 centimeters per minute. And that's specifically when the height is equal to 4. So essentially, that's all the information we've been given in the question. And what we'd like to find out, should come back to the top, what we'd like to find out is how much liquid do we want to add to the cone so that the depth stays at a constant 4 centimeters. So what I've done next is say, well, since I have two rates of change, I've got dV dt and dH dt, I'd like to find some kind of relation between those. So I've made a chain rule, which would be dV dH, which currently we don't have yet, and the two values that we do have. So dV dH multiplied by dH dt is equal to dV dt, and that's just using the chain rule. I'm also noticing that all of these expressions are in terms of V, H, and T, so I don't really want to have R and L in my equations. So here I've just drawn the same diagram again, but a little bit differently. So this is showing sort of the level of the liquid, which is not at the full height, it's somewhere lower down. And that's going to depend on how much liquid is in there. So our H, R, and L are closely linked together. And just using some trig ratios again, I've found that R is the same as H over 5, and L is the same as root 26 H over 5. And that's just using the fact that we know tan and cos from the original shape of this cone, and that's related to that angle. This angle is not going to change, so that's why I've used that. Like I said, I don't have dVdH at the moment, but we do know the volume of a cone is 1/3 pi r squared h. And since I've found an expression for r in terms of h, I've plugged that in here. That gives me a new formula for the volume, which I've then differentiated to give dVdH. So since I've now got dVdH and an expression for dH dt and dV dt, I'm just going to plug those in. So that's this expression here. Oh, sorry, this equation. And at the moment, what I'd like to work out is the rate constant K. Bearing in mind that we do know that H is going to be 4, that was given in the question. So I've substituted everything into that chain rule. I've also changed R and L into terms of H because we found those earlier. And doing a little bit more algebra, I end up with K as this value 0.117 and so on. What we actually want to find out, though, is that the total amount of change in the volume of liquid should be equal to 0 so that the height doesn't change. So we want to have the rate of change of the volume equal to 0. So we do know that the rate of change is going to be the amount of liquid going in minus the amount of liquid going out. And if that is equal to 0, then these two rates of change should be equal to each other. Again, I'm just using the same formula for the rate of change of volume leaving the cone. And we already found a value for K, which is this value, pi. This one is R, this one is L, and we're supposing that H is equal to 4 from the question. If we calculate that, we end up with 1.2 cubic centimeters per minute. And this is what we would expect since a rate of 1 cubic centimeter per minute was allowing the liquid level to decrease. We were expecting an answer to be just slightly bigger than 1, which this is. Hope that helps. Bye.